We present D-NLC, a modular control framework utilizing local proprioceptive feedback to modulate joint-level CPG signals to produce emergent locomotive behaviors. Previous works such as MantisBot lack rigorous multi-legged full-body physical robot hardware testing. Similarly, the Hector robot and Drosophila bot having multi-legged physical testing cannot handle extreme perturbations such as amputation. These systems utilize a centralized controller to emulate the distributed nature of neuron clusters, which does not guarantee the feasibility of deployment on a decentralized architecture. To address these challenges, our contribution focuses on imitating stick insects' CPG and sensory feedback structures on a distributed embedded robot. As shown is our system parallel to the stick insect distributed neural structures. We also develop practical implementations for neuron structures presently unknown within biological research. D-NLC coordination can be divided into two categories, intralimb and interlimb pathways, both modulated by joint-level proprioceptive feedback and loosely coupled CPGs computed inside each joint's embedded system. Our work demonstrates D-NLC's feasibility on a flat walking hexapod that is able to extend to withstand internal and external perturbations without additional tuning. From our experiments, our methods could generalize to uneven terrain and amputation conditions on physical hardware and simulation with little to no change in the controller. Results demonstrate that D-NLC adapts well to internal and external perturbations while maintaining a gait pattern and forward velocity. Using percentage velocity decrease, we observe a 31.3 better performance with D-NLC compared to a predefined gait centralized controller, which is statistically significant for large perturbations. We also evaluate adaptability through emergent behaviors, which can be represented by phase difference and stance duration. D-NLC shows emergent gaits coordinated by phase differences amongst legs. The phase difference causes alternation of neighboring legs' motion, improving stability and reducing trajectory deviation. Individual leg stance duration was observed to indicate direct proportionality with joint load, and thus increasing stability and reinforcing forward motion. The validity of both of these emergent behaviors are supported with biological observations. Limitations include non-adaptive height control, unintentional turning due to imperfect coordination amongst legs. Future work includes adding tarsus sensory pathways with force sensors, improving leg coordination by tuning interlimb weights with coupling strength, and implementing other behaviors such as curve walking onto hardware. In summary, D-NLC is a practical implementation on a distributed system, which is robust to perturbation and displays adaptation with emergent gaits and coordination. We hope this contribution will add to the research on improving robotic functionality through biological inspiration to overcome technological limitations.